Now we come to some more tricky definition. It's called conditional typical sequence. Now we consider a conditional distribution P y under the condition x and define it for sequences. We define Pn y under the condition x, yn under the condition xn as the product of Pyx of yi under the condition xi. And then we define the typical sets Pxy under the condition xin as all sequences yn such that xn and yn are jointly typical. First, what we observe is if that this set is empty if xn is not a typical sequence. How we can interpret this? So what we can do, we can think about a system or a channel perhaps, where we have the probability Pyx that we receive the letter y if we send the letter x. If this is a probability distribution for the channel or the system. Now we send some sequence over the system. Let's assume we send xn, which naxn over the channel. So it have now naxn denotes how many times a appears in xn. Now we will look at the received sequence. If we multiply now naxn by the probability of B condition on A, then the received sequence will contain so many y's in those positions where the original sequence xn has the letter A. And then with high probability xn, yn is jointly typical. Yes, so what we did, we defined somehow when we have a channel and sent there a typical sequence over it, that it's again typical concerning the resulting probability distribution. We have the following theorem for that. Perhaps we directly look at the approximation part. So the first thing, the 35, that's exactly the definition we have again. That's the same we have before, that the probability which we have defined, yn conditionally on xn, is approximately 2 to the minus n h of y conditional on x. The next thing is the number of typical sequences. That's in principle exactly the same proof we did before. It's approximately 2 to the n h of y and conditional on x. Then here we look at the probability that yn is an element in this set here under the condition that xn is equal to x small xn. This goes to 1. And the last thing is the probability that yn is element in the typical conditional thing is approximately 2 to the minus n of the mutual information of x and y. So if you look at this, I told you already the first thing is more or less the definition. The second and third is a little bit more complicated. We need the Chernoff bound and also the Pinsker inequality. So Abdallah will do this in the lecture. And the proof of number 38, it's very similar like we did before. So again, we estimate the probability by the sum of the single probabilities. We use the fact that then Py of yn is typical and estimated by this, and then we have again the sum of the same probabilities, and then we can estimate this. But we can use the estimation of 37, insert it there, and again we remain with the mutual information. If you look at some examples, what happens if X and Y are independent? Then we can approximate 37 and 38, and from both we get the expected result that the probability of Ym of the typical sets is equal, goes to 1. The next example is if X and Y are the same. Then again, we get the same thing, that Ym is there, is approximately 2 to the n of h of x. Both results are not so surprising, because we know that this goes, that xy goes to 1, and we also here we know that the typical sets goes to 2 to the nh of x. And somehow we are computing the probability of the event that xn is equal to xn for some typical sequences xn.